Everyone tells you to run the bigger high precision model for better answers, so I tried on a normal 8 GB laptop, and it wouldn't even load. So the question stopped being how much quality the small model gives up, and became a blunter one. Of the three sizes, which can a cheap machine actually run at all? Before any numbers, the usual promise, every result here is reproducible. By the way, if you want to run these benchmarks yourself, I've linked the raw JSON and React code I'm using down in the description for free. Here's the setup, and the one rule that keeps it honest. Nothing changes but the precision. The same 8 billion parameter model, the same weights everyone runs, stored three different ways, 16-bit, 8-bit, and 4-bit. The same 15-task exam from a few episodes back, with deterministic graders, temperature pinned to 0, and no second AI judging the first. The same 8 GB laptop. The only thing I touch is how many bits each weight is stored in. So whatever happens, the quantization did it. And the quantization is simpler than the word makes it sound. Here it is in a line. Every weight is just a number, and full precision stores each one in 16 bits. Quantizing rounds those numbers to fewer bits, 8 then 4, so the file shrinks by roughly half, then half again. The same model with coarser numbers. The grader is the same deterministic check from the exam episode, so the only question on the table is what those coarser numbers cost you, starting with whether they even fit. Start with the number that decides everything else, size. At full 16-bit precision, the 8 billion model is around 16 gigabytes. Quantized to 8-bit, it's around 8.5, and 4-bit just under 5. Now hold those against an 8 GB laptop that also has to run an operating system, a browser, and whatever else you got open. And you already see the problem. Only one of these three leaves any room to breathe. So here's the first verdict before a single exam question is graded. 16-bit at 16 gigabytes was never going to fit the 8. That one's obvious. But here's the part that surprised me. 8-bit didn't fit either. At 8.5 gigabytes on an 8 GB machine, it spills straight into swap slowed to a fraction of a token per second. I mean frozen, not slow, and then timed out. Two of the three sizes everyone treats as the quality options are off the table on a cheap laptop before you even start, which leaves exactly one. On an 8 GB rig, the 4-bit model isn't the budget compromise you settle for. It's the only one that actually runs. So the real question was never how much quality does 4-bit give against the bigger ones. It's the one that actually matters when you own a cheap machine. Is the only quant that fits actually good enough? So I gave it the exam. The 4-bit model, the only one that loaded, set the same 50 tasks the local models did a few episodes back, and scored 87%. 13 out of 15, and the two it missed were multi-step arithmetic, exactly the weak spot we found before. Give it a calculator, not more bits. So the one quant that fits a cheap laptop isn't a sad little fallback. It's genuinely capable. And it isn't just that the 4-bit fits, it actually works. It ran the whole exam at about 11 tokens a second. Usable, comfortable, the kind of speed you'd sit and work with. Put that next to 8 bits fraction of a token per second on the same machine, and it stops being a quality versus speed trade-off. One of them answers, the only one chokes. On this rig, there is no contest, because two of the three contenders never made it to the starting line. So here's the thing, the advice gets backwards. Run a higher precision build for quality quietly assumes you have the memory to hold it. And on a cheap laptop, you just don't. The real ceiling isn't accuracy, it's RAM. 4-bit isn't where you compromise on quality. It's where the quality and memory finally fit in the same machine at 87%. So measure exactly what loads on your hardware before you argue about the last few points on a score you'll never get to run. Now, there's a smarter version of this I want to test, and I owe the idea to a viewer. Shout out skmineforever in the comments. I'm pretty sure I said that right. Instead of taking a finished model and running down afterwards, you can quantize it during training so it learns to live at a low precision. It's called quantization-aware training, and it's supposed to keep more of the brain ordinary 4-bit gives up. The catch is the exact one this whole episode is about. The build he runs needs 16 gigabytes, more than this laptop has. So that test is coming on a machine that actually can hold it. The wall doesn't disappear, you just need bigger room. Here's the verdict, measured rather than guessed. On a cheap 8 GB laptop, the better quants are at Mirage. 16-bit can't load, 8-bit swap thrashes and times out, and the 4-bit model is the only one that actually runs, at 87% on a real graded exam, and fast enough to work with. So don't chase a higher precision build for a quality it can never deliver, because it never does, and it never fits. Run the one that loads and measure it. The data and the code are linked below. Next time, now that we know what fits, which jobs are even worth keeping on a local model, and which should you just pay the cloud to do, measured per task? This has been the Validation Set. Subscribe, and and I'll see you there. Thank you for listening.